Hey everyone, I'm going to make a quick recording to help you with this Khan Academy practice set. It's all about differentiability and continuity. The key concept to know is that if you have some function that's doing something, I need to get the pen, that's doing something interesting like this, and then it transitions as a piecewise function to another function. It might go like this as a straight line. It could go, I don't know, like this as part of a parabola. It could do something even like as an exponential. But at this point of transition right here, in order for it to be differentiable, the derivative from both sides need to agree. Therefore, at that point, check each part to see if the derivative is the same. So it's all about the connection point being equal and the slopes being equal. Okay, so here, clearly the cutoff is at 3. So whatever this graph is, it'd be like 3 units over. We've got, it looks like a parabola that's just going through the origin. I like this example because it's really simple. It's a parabola going through the origin, and then here it transitions to a straight line that's got a slope of 6 going upwards. If it continued downwards, it would go through an intercept of, what is that, not -9 down there, okay? The question is, looks continuous. Let's check it out. I've drawn it that way. If I plug in 3 squared is 9. I plug in 3 times 6 is 18, minus 9 is 9. So this point here is 3, 9. So it's definitely continuous. The question is it differentiable throughout? So what is the derivative right here at this point? What is the slope of the tangent line? Well, the little shortcut that I think we all should know is the power rule for this. You could use the limit definition. We could do h go to 0 method and work out the derivative. If you've done this a bunch now, maybe you've noticed the pattern that for every x squared, we get the 2 kind of coming out front in a sense, and the degree going down by 1. So the derivative of x squared is simply 2x. So f prime of x in this case would just be 2x. You can certainly verify that using the limit approach, but this is the shortcut known as the power rule. If there's a multiplier out in front, like if it says 5x squared, you just take the 2 and you multiply it by the 5, because our limit laws, same as our derivative law in this case, we can remove the 5, find the derivative, which in this case is 2x, and then multiply the 5 back in. So 5 times 2x would give us 10x. So there's our derivative. Okay, so now where's the point we're doing this derivative at? Oh yeah, it's 3. So when I put the 3 in there, 3 times 2 is 6. The slope of the tangent line to this parabola right there would be 6. Well, guess what? What's the derivative of this? The derivative is just the slope of the tangent line, and it is a line, so it is just the slope. So hopefully that will be an easy way to conceptualize the fact that for any given line, the slope of the line is just the slope of that line. So they both are 6, so the slopes agree. When the slopes and the points are agree, it is both continuous and differentiable. Okay, so next question. Then let's see if we can talk our way through this one. I can take each piece and find the derivative. This is going to be 2x for that derivative. Like I said before, this is just going to be the slope if this was a line. So that's -5 would be the slope of that line. That's the derivative. At 3, the slope here would be 2 times 3 is 6 minus 5. The slope here of this part is 1. So g prime of 3, we'd say, equals 1 for the slope. I just can't write it. It's too tedious. What is the slope here? Oh, the slope here is -3. So it looks like these two slopes do not agree. Oops, I'm sorry. I'm talking too fast. Yeah, no, I've got that right. Not talking too fast. So the slope there is 1. The slope there is -3. Perhaps the points agree. When I plug in 3 right there, 3 times -3 is -9, plus 2 is -7. When I plug in 3 right there, I get +9, but -15 is -6. Minus 1 more is also -7. So these two bits connect. They are continuous, but they are not differentiable. Okay, hopefully that helps. Good luck, everybody.